Welcome to the last lecture. Hello all, welcome to the last lecture number I think 43 or 44. Okay. Okay. So in the last lecture we were looking at complexity of problems. In fact, we considered four different problems: vertex cover, independent set, click, and satisfiability. We saw that these problems are kind of related to each other. Or in other words, we saw that vertex cover is in P if and only if independent set is in P by just seeing that the complementary set of a vertex cover is an independent set. So in other words, a graph has a vertex cover of size k if and only if it has an independent set of size n minus k. Okay. And by considering the complementary graph, we saw that independent sets are nothing but clicks in the complementary graph. So in other words, click is in P if and only if independent set in P. Further, by transitivity, that is taking an instance of vertex cover, transforming it into an instance of independent set, that is input instance of independent set, by just changing k to n minus k, and then considering the complementary graph, changing it to an instance of click. So we see that vertex cover is in P if and only if click is in P. In the last lecture, we also gave a transformation where given a 3CNF formula, that is an instance of 3 satisfiability or 3 sat, we transformed it into an instance of vertex cover. That is, given a Boolean formula, we constructed a graph such that formula is satisfiable if and only if graph has vertex cover of certain size, which was 2m plus n. Okay. So number of vertices in the graph G phi is 3m plus 2n, where m is the number of clauses and n is the number of variables. Okay. So I left it as an exercise to show the other way around. That is, given an instance of vertex cover, that is a graph and a parameter k, we can construct a Boolean formula, in fact a CNF formula, such that graph has a vertex cover of size k if and only if the Boolean formula is satisfiable. Okay. So yeah, we will not really discuss this. So that effectively shows that sat is in P if and only if vertex cover is in P. So while these three relationships are like, one can argue that okay, they are a different variants of the same problem or interrelated problems, whereas we saw that this is slightly, I mean, much unrelated problem or literally unrelated problem is being related. So a problem over Boolean formulas or CNFs is related to problem over graphs. Okay. So this kind of leads us to looking for common structures among these problems. Okay. So we, based on that, we defined the small witness property. So we say that, so this is about decision problems. Let A be a decision problem. We say that A has small witness property if there is a decision problem B which has efficient algorithm, that is, which is in the class P. So P is set of all problems which admit polynomial time algorithm, such that for any input, so for all x, x is in A, that is x is an S instance for A. So remember that we are only considering decision problems now. If and only if there is some string of length at most n to the c, so the constant is quantified in the definition itself. So there must be a constant based on A. The constant depends on A as well as probably B too, such that x comma y is in B. So you concatenate the string x with along with y, probably with some delimiter. We should be getting a string in B. Okay. So this is if and only if characterization. That is, if x is not in A, there should be no such y. So for every y of length at most n to the c, xy should not be in B. Okay. So yeah. So let's look at our problems and see what are small witnesses. Okay, so what is the language B and what is uh, the witness for the problems that we have considered in the class. Okay, so problem, that is A, B, witness. Sorry. Witness B. So remember that a decision problem, we can always write the S instances of the problem as a set. Okay, so we'll treat A and B as sets. So that is why I've chosen this notation. Okay, so this is basically saying X is an S instance for A. Similarly, XY is an S instance for B here. Okay, so I'll use set notation. So I'll write this witness and the problem as sets. Okay, so problem A is vertex cover. Let's start with vertex cover. So in set notation, this will be G comma K. G has a vertex cover of size K. Okay. So this is the problem A. I'm writing it as set. So all S instances are included in the set. Okay. So witness S subset of V. Cardinal of S is K. S is a vertex cover of G. Okay. So that is a witness. Okay. So now what is a witness language? So we'll call this as a witness language. Okay. So what is a witness language here? So witness language is, so in this notation it should be X comma Y, right? So what is Y here? So Y is a subset which happens to be a vertex cover. So now how do we write the witness language or witness set? G K comma S such that S kernel of S is K and S is a vertex cover of G. Okay, that is a set. Now is B in P? So given a graph and a value K and a subset of vertices, to check if the subset is a vertex cover, all we need to do is run through all edges and see every edge has at least one of its endpoints in S. So this is easily verifiable. And what is the size of the witness? Size of the witness is at most n. If you write in bit notation, assuming that vertices are labeled 1 to n without loss of generality, so the label of a vertex can be represented in log n bit. So at most n log n bits. Okay. So length of the witness, length of length of witness set is equal to k log n log n. So binary representation. You can even represent it in n bits by just considering this as a 0 1 vector of length n. Okay. So yeah. So similarly for click, problem GK, G has a click of size K. So I had written in the problem definition n by 2. I'll just generalize it of size K. Okay. So I'll leave it as an exercise for you to figure out what is the witness and what is B. Okay. Please write it. So exercise. Similarly for independent set, define the language. Leave this as exercise. It's pretty much straightforward from there. Okay. Now for satisfiability, what is it? Formula phi is satisfiable. Now witness an assignment A in 0, 1 to the n such that phi evaluates to 1 upon it. So what is the witness language? Phi A such that phi of A is 1. And we need to put the condition that okay, phi is a CNF and so on. I've just written it in short. Okay. So all these four problems, decision problems, or in other words, languages, they have the small witness property. Okay. So that is one commonality between these four problems. Now, it turns out that most of the hard to solve problems, when I say hard to solve problems, problems which are not known to have efficient algorithms. So like we discussed in the last two lectures, all of these problems admit algorithms that run in time 2 to the n, maybe slightly less but comparable. Okay, sometimes it could be n choose k and so on. Okay, but if you choose k sufficiently large, that is n by 2 or suitably, then this is omega of or 2 to the omega of n. Okay, these algorithms. So now the question was like, are there polynomial time algorithms for these problems? Okay, so we saw that the interesting fact is it's enough to give polynomial time algorithm for one of them, then all of a sudden you get polynomial time algorithm for the remaining three, right? So whichever, it does not really matter if you give this for vertex cover, then for all three other you get a polynomial time algorithm. So that way they are interrelated. Now looking at their structure, they have one nice property, though we don't really have a solution, that is an algorithm which solves the problem in polynomial time. We have the following property, that is they have short witnesses. By short I mean polynomial length witnesses, which are verifiable in polynomial time. Okay, so these are basically characterized by witness problems or witness languages. So for each problem that we have considered, there is a corresponding witness language. Okay, so yeah, so now we define the class NP. This is standing for non-deterministic polynomial time. Okay, so a decision problem A is said to be in NP if it has the small witness property. Let's be more explicit, that is there is a B in P and C greater than 0 such that for all x, that is valid input, okay, so any legitimate input, if you are having a graph problem, then for all graphs, for example, okay, x is in A if and only if there exists a y in 0, 1 to the n to the c such that x comma y is in B. Okay. So in the last lecture, I was talking about problems being intractable. So by intractability, we mean problems that admit, not known to admit efficient solutions. Okay, not known to have. not known to admit. Okay, so we cannot really prove that okay they don't have efficient solutions, that is efficient algorithms, but we don't really have. Okay, so such problems are intractable problems. So the notion of intractability is measured through so tractable are those problems which have which admit polynomial time algorithms or efficient algorithms. Okay, so we measure intractability through this. So we call this class as NP or non-deterministic polynomial time. By class I mean class of all problems. That is set of all problems. Set of all problems is called as a class. Okay, so this becomes a complexity class now. So remember that P we defined as class of all problems that are decidable in deterministic polynomial time, I mean usual polynomial time. Okay, so these are non-deterministic polynomial time. So I didn't really say what is non-determinism here. So non-determinism, the origin, it has its origins from the concept of non-determinism. Most of you would have seen in an automata theory course or a theory of computation course. So you can imagine, so see here the point is there is an existential characterization, right? So that's why I meant here as existential crisis. Okay, so there is an existential characterization here. So there is an existential quantifier. Okay, so any description of a problem, so it's basically you can see it as membership in this class A or this language A. Okay, so when I say membership, that is S instance. Okay, is characterized to, so there exists something so that something happens. So this something happens is easy to verify. So there exists something is not easy to verify. But if somebody gives this witness, you can verify it. Okay. So this existential quantification, you can view it in the following way. Okay. So you can imagine, so there is a player or there is someone who is trying to provide a proof or a guess a proof. Okay, so you can just imagine, okay, there is a student and a teacher. So student is trying to come up with the proof. So student basically guesses the proof. Okay, so this you can imagine it as a proof of a theorem or a statement or whatever. What is the statement here? Statement is saying that X is in A. Okay, now the teacher has to verify. So assuming that the teacher is very well learned and knowledgeable, so teacher manages to verify provided the proof is short, maybe 1 page or 2 pages proof. Okay, so this idea is well captured with the concept of non-determinism. So you might have seen in non-deterministic finite automata, uh, so what is extra compared to a deterministic finite automata is transitions. So for the same current state and same symbol, right, you can have multiple transitions. Okay, so basically you have choices. So how is the notion of acceptance defined? So notion of acceptance is defined by saying that okay, if there is a path from the start state to a final state, one of the final states, then you know that NFA accepts. That's the definition, right? So you can just imagine. So basically, describing acceptance is basically you're saying there exists. So instead of a string, you're saying a path. You can represent a path as a string, right? Based on the choices. For the first node, I take the first outgoing vertex edge. Similarly, second node, second, third, first, and so on. So you can describe it as a string, right? So it's essentially saying that there exists a path is equivalent to saying that there exists a witness. So you can imagine in an NFA, acceptance is described by a path or not a path, in fact, a walk, right? So that's a run of the automata. Okay, so so the walk, it's not a path. I take it back because you can revisit nodes arbitrarily because finite state automata will have a small number of states compared to the input. So it's basically you're guessing a path, right? So you can imagine this existential quantifier being the process of guessing something. Then you verify. How do you verify? You walk through and match it with the input string so that okay, these are valid transitions, and ensure that you reach a final state, right? Final state which is accepting. Okay, So in a similar process, I mean, in a similar manner, we can define non-deterministic Turing machines. Okay. So then what happens is problems that admit this characterizations are this kind of characterization are exactly those which can be accepted by a polynomial time bounded non-deterministic Turing machine. Okay. So if a Turing machine is say n to the c time bounded, I am not defining what is the time, basically number of steps, nothing else. Okay, number of transitions applied, number of times transitions are applied. Now, if it runs in say n to the c time, you can encode each choices made. Say at the first transition there were k choices, out of which we may choose one of them. So using log k bits, you can represent them, right? So a Turing machine, again, it's finite state, so the number of states is bounded compared to n. So log k is a constant number, right? So constant number into whatever is the running time, those many bits are enough to represent uh, the choices made through non-determinism. Okay, so yeah, originally NP was defined through non-determinism. I'll just write it without really going into details because it's not our purpose. Okay, so for us this characterization is kind of enough, more than enough. But for the sake of it, I'll just write. So NP is the class of all languages that is decision problems that are accepted by polynomial time bounded non-deterministic Turing machines. Okay, so this is the formal definition of NP. Both are equivalent definitions. I mean, people from logic background, they basically defined NP through this way, and people from computational background, basically algorithmists and those who work with Turing machines, they defined it this way. So they kind of concluded that okay, both are the same things. I mean, both represent the same thing. Okay, so yeah, traditionally in complexity theory course, people introduce NP through this way, and in a logic based course people will introduce this way, and both the courses will see this equivalence. Okay, so we'll not really go into the equivalence and so on. Okay, we just stick to this definition. This is easier to follow. We don't have to define what is a Turing machine and so on, but this is something all of you should know. Okay, so once you have this in mind, you know what this n is, because otherwise many people tend to uh, remember this as non-polynomial, which it is not non-polynomial, it is non-deterministic polynomial time. Okay, so that is what NP stands for. Okay, so now so this is not it. Okay, so we just looked at 4 problems which were kind of intractable. They admitted exponential time algorithms, but we have no knowledge of whether there are polynomial time algorithms for them. But surprisingly, we saw that obtaining polynomial time algorithm for one of them is equivalent to obtaining polynomial time algorithm for all the remaining 3. So that way they are interconnected or interrelated with respect to polynomial time solvability or existence of efficient algorithms. Now, then we saw that they have small witness characterization, all 4 of them. So we gave a name to problems that admit small witness property. Okay, so we call them as NP. Okay. Now, so what we have shown, so I'll write it as a corollary, as we see independent set click sat, in fact also 3 sat are in NP. Okay. So now one question people try to address is like, okay, now it looks like okay at least 3 or 4 problems, but not only them, there are lots of other problems which also satisfy similar property. They're also in NP. Okay, so people try to see, okay, so what is a structure? I mean, okay, so what is the hardest among them? What do I mean by hardest? So is there a problem in NP such a way that if you obtain polynomial time algorithm for that problem, then you would have obtained polynomial time algorithm for all of other problems. Okay, so is there a hard problem in NP? That is there an A in NP such that A is in P implies whole of NP is in P? That is for all L in NP, L is in P, implies L is in P. Okay. So such problems are called NP hard problems. So answer is S. Such problems are called NP hard problems. Okay. So we'll define what is NP hard formally in short. Okay. So for that we need to define a formal way of comparing. Okay. So we need to give a name for what we did here. So we transformed VC to independent set, click to independent set, or vice versa, and hence VC to click, and then SAT to VC. And as an exercise, we also have the task of converting a vertex cover instance into a satisfiability instance. Okay. So now how do we formalize that? So we formalize these through reductions. So let A and B be decision problems. We say that A reduces to B. For simplicity, I'll just use this notation: A less than or equal to B if there is a polynomial time procedure algorithm, let's call it as F, such that for all x, so this procedure outputs a value. Okay, this output strings. By using the term string, I'm just representing everything. They might output a graph or a matrix or whatever. Okay, it could be any object. So remember that any input or output, input to a computer or output of a computer, you can imagine it as binary strings or strings over some alphabet. Okay, so that is why we use the term string. So for all x, x is in A if and only if f of x, this is the output of x, sorry, output x on input, output of f on input x, f of x is in B. Okay. So example, so vertex cover reduces to independent set. So what is x there? X is gk, f of gk is g n minus k. Now independent set reduces to clique, f of gk is equal to, sorry, g complement k. This is a complement graph. Okay. Similarly, sat 3 sat reduces to vertex cover, f of phi is g phi, comma, what was it, 2m plus n. This is the value k. Okay. So that way, so we have just formalized the way we the comparison that we have obtained these classes. Okay. So one observation is exercise. So prove that is transitive. That is, if A reduces to B and B reduces to C, that implies A reduces to C. Okay. So it's fairly straightforward. I mean, not very difficult. It basically follows from the definition and the property of polynomial time computation. Okay. So yeah, so this is the notion that we are going to use to characterize hard problems. Okay. So remember, our question was, are there hard problems in NP, or is there a hard problem in NP? That is there a problem A in NP such that A is in P, that is showing that A has polynomial time algorithm? That means that whole of NP, that is any problem in NP, also has polynomial time algorithm. See, this subset of problems that we have considered, in fact, they admit. Okay. So except the relation between SAT and 3 SAT, which I didn't really specify, I'll mention it without proof. I'll give it as an exercise for you to read. So they have the property that if you show that one of them is in polynomial time, all of them are in polynomial time. Okay. So this is not specific to these 4 problems. In fact, it is a property of the whole class NP. Okay. So the groundbreaking result in this direction is by Stephen Cook, and also later on improvised by Richard Karp. So theorem, and this was also proven parallelly by Leonard Levin. Okay, so it's called Cook-Levin theorem. Okay, 3 SAT is NP hard. Okay, so what do I mean by NP hard? So A in NP is said to be NP hard. It's exactly the notion of hard problem that we stated here. Okay, that is, if for all B in NP, B reduces to A. Okay. So what does this mean here? It's equivalent to saying for all B in NP, B reduces to SAT. In fact, 3 SAT. Okay, not just SAT. So in other words, this basically says if any one of us obtain an efficient algorithm for 3 SAT, by efficient I mean polynomial time algorithm for 3 SAT, then whole of NP would have polynomial time algorithm or would admit polynomial time algorithm. Okay, so we'll need one more notation here. A problem A is said to be NP complete if A is in NP and A is hard for NP or NP hard. Okay. So corollary of Cook-Levin theorem is, in fact, it's also called Cook-Levin theorem. 3 SAT is NP complete. Okay. Yeah. So this is the most fundamental or breaking result in complexity theory or even in algorithms and complexity. In fact, this is the statement which actually led to the development of what is known as complexity theory today. The whole area of complexity theory is founded upon this result of Cook and Levin. Okay, so in fact, there are several areas or research areas which basically look at NP-complete problems and they want to obtain efficient algorithms. May not be polynomial time, but there are, so with some limitations. Okay, may not be exact solutions, maybe approximate solutions, maybe better exponential algorithms and so on. Okay, so yeah, so now we are, so let's just have a closer look at it. Okay, so now let's come back. So what we know is VC reduces to independent set and so on. 3 SAT reduces to VC. What does it mean? So any language in NP, by this theorem of Cook-Levin, we are not going to see the proof. Okay, proof is beyond us for now. Okay, those who have done computability and complexity might have seen a full-fledged proof of this statement. So what we have is any problem in NP is reducible to 3 SAT. But what we have here is 3 SAT reduces to vertex cover. So what does it mean? So we have 3 SAT reduces to VC, and for all B in NP, B reduces to 3 SAT. Therefore, for all B in NP, B reduces to vertex cover by transitivity, which I left as an exercise. So remember here, there is an exercise, right? So prove that this less than or equal to relation or reducibility relation is transitive for all languages. Okay, that is A is reducible to B and B is reducible to C implies A is reducible to C. Okay, so by that transitivity property, what we have is vertex cover is NP hard. In fact, vertex cover is an NP, so hence it is NP complete. Okay, not only that, so if you look at these equivalences, but then it's vertex cover reduces to what? Independent set, and independent set reduces to clique, or in other words, independent set and clique as well are NP complete. Okay, so as a corollary again, vertex cover click independent set are NP complete. Okay. So now that is the property of these four problems. So all these four problems, in fact, SAT is also NP complete when you don't have limitation of 3 on the clause size, that is number of literals in every clause. Okay. So all these four problems, they are kind of hard for NP. They are kind of essence of NP. Okay. So the area, in fact, exploded into huge I mean, kind of the research area of complexity theory kind of exploded soon after Cook's proof of NP completeness. In fact, there are thousands of problems which are known to be NP complete. Okay, it's not just these four problems. There are lots of problems. So what I'm going to do is I'll just give a way of showing NP completeness. Okay, of a given problem, and then towards the end I'll tell what are the different methods or areas that explore ways of coping up with NP completeness. Okay, so how do we deal with NP completeness? So why NP completeness so bad? So NP completeness, it basically says among these problems, these are all hard problems. That hard problem means must be difficult to obtain solutions, right? I mean, that's a reason why we use the term hard. Okay, basically hard is meant to say that it's hardest among in this class. NP hard means hardest among NP. Okay, with respect to obtaining efficient algorithms. Okay, so let's just see how to show a problem is NP complete. A is NP complete. So usually we divide this into two steps. Step one, show that, and this can be interchanged, there's no specific order, it could be step two also. Show that A is in NP using small witness. You basically show that A has small witness property. Step two, pick some NP complete language or problem, B, and show that B reduces to A. Okay. So all we need to do is show that A is in NP and pick some already NP complete problem. So that's what happened here, right? So see, we used Cook-Levin theorem that 3 sat is NP hard, or in fact NP complete. Okay. Now, if you show that 3 sat reduces to some problem A, okay, then you know that A is NP complete. That's exactly what we did for vertex cover, independent set, and click. All three are NP complete because of this virtue or this property. Okay. So now to show that a given problem is NP complete, all you need to do is show that it's in NP and then pick a suitable NP complete problem and show that it reduces to A. Okay. So I'm going to conclude this lecture with one example reduction. Okay. So two examples are basically given as exercises. Okay. So basically you have to choose probably an instance of satisfiability or something else, show that it reduces to the given problem there. Okay. So today I'll consider one more example. So one non-trivial example was already SAT to vertex cover. So the second non-trivial example is a special case of decision version of the knapsack problem. We call it as subset sum. So let's consider subset sum. So input is x, a finite set of non-negative integers, and a target t, again non-negative integer. Okay. Output s if and only if there is a subset x prime of x such that summation a in x prime a is equal to t. That is there a subset? That is, there is a that sums exactly to t. So you can see that this is a decision version of knapsack, but restricted to integer values, non-negative integer values. A knapsack problem is you are given a set of values, okay, or set of weights or whatever, yeah, set of weights or volumes of objects. Now you want to see that what is the optimal. So given a target bound or whatever, so a value of k, so what is the optimal packing that you can do? Or sometimes you may not even be given a k. So, okay, so you have to get a subset of objects which basically maximize, okay, value. So here it's a restriction where you have a target value, you have to exactly match the value. Okay, so this is a decision version. We call this as subset sum. Okay, in some context, I think it's even called as integer knapsack or whatever. Okay, so we show that subset sum is NP complete. Is NP complete. Let's prove it. So step one is subset sum. So let's call this as S sum. S sum is in NP. I'll leave it as an exercise. So what is the witness? So witness is a subset. Okay. What is the verification procedure? So add the values in subset and see if it is equal to t. Okay. So that is it. Step two. Show that S sum is NP hard. Yeah, so this is the most non-trivial part. Okay, in most of the cases, the first step is rather easy. There are instances where the first case is non-trivial, but in most of the cases, it's very easy. Okay, and the second part involves two sub steps. Okay, first is choose a suitable. That is a non-trivial. Okay, so you need to choose a suitable B and then show that B reduces to A. This usually happens by trial and error. So what you see in the books are basically outcomes of several iterations of trial and error and so on. Okay, in principle, it can be any problem, any NP complete problem will reduce, but sometimes the actual problem really helps. Okay, so here you could think of trying 3 sat. but it's easier to work with vertex cover. Okay, so I'll give a simple reduction from Jeff Erickson's book. Okay, so we show vertex cover reduces to subset sum. Okay, so let gk be an input instance of vertex cover. So we need to transform. So we want an x and t such that gk is an s instance of vertex cover if and only if xt, remember x is a subset of non-negative numbers and t is a value, xt is in subset sum. That is, the output of subset sum should be s for x comma t. So all we need to do is, given a graph, we need to construct a set x and a target value t such that G has a vertex cover of size k. See, we are not exploring the graph to see vertex cover already. Okay, this transformation, basically looking at the graph, you should be able to produce this subset. But the property is G has a vertex cover of size k if and only if x has a subset which sums to the value t exactly. Okay. Yeah, so this again, the reduction is, once you see it, it looks simple, but it's very non-trivial to come up with. It's not that straightforward, unlike the ones that we have given in exercise, which are pretty much straightforward reductions. Okay, so here what we do is basically obtain encodings. Okay, so the idea, one number for each edge, every edge gets a number, and for each vertex. Okay, so we associate numbers for each edge and each vertex, then add this as a set. Then we'll set a specific target value, and we see that the target value is equal to, I mean, there is a subset which matches the target value if and only if graph has a vertex cover of size k. Okay, so that is all. So let's see the values. So for each, so label the edges 0 to m minus 1 arbitrarily. Okay, we are assuming that number of edges is, so g equal to ve, and number of edges is m. Okay, so now define ae is 4 to the e. So e is a number from 0 to m minus 1. Okay, so you're assuming that edges are numbered. So when I say ae, basically the number. Okay, so 4 to the e, so 4 to the number represented for the edge. Okay, yeah, I hope there is no confusion. Okay, and for all v in v, av is the following number. Okay, which is 4 to the m plus, so now you look at set of all edges. Okay, so e such that v e is incident on v. Okay, you just sum the corresponding values. Basically you look at v E1, etc., etc. So basically write this as, so 4 to the E1, sorry, yeah, 4 to the E1 plus 4 to the E2, etc., etc., etc. This is the summation. Okay. Now the set X is nothing but X is AE, E in E, union AV, V in V. So cardinality of X is number of edges plus number of vertices. Okay. So one thing, I mean, I hope I didn't confuse. So here when I say AE, see, we said that we number the edges, right? So edges are numbered from 0 to m minus 1. So if the edge E has number say 10, then this will be 4 to the 10. Okay, so that's what this means. So this is number corresponding to E. Okay. So I just used E so that there is no confusion. I mean, otherwise I'll have to say whatever EI. If E is equal to EI, then I. It's the same thing. Okay. Yeah. Now, what is the target value? So target T is equal to K into 4 power m plus summation 2 into E equal to or I equal to 0 to m minus 1 4 power I. Okay, that is all. Claim GK is in VC if and only if XT is in subset sum. Suppose, so the forward direction, so in if and only if relation, you just prove both the directions. Okay, so to show that GK is in VC implies XT is in subset sum. Okay. So S be any V such that cardinality of S is K and S is a vertex cover. Okay. Now, so X prime B S union AE such that edge E is incident on exactly one vertex from S. So what you do is the claimed vertex cover S. So these the corresponding numbers AV where V is in S, plus what you do is you just look at edges which are go out. You take the corresponding numbers. Okay. Now this should sum to the value T. So what is sum of X prime is equal to, so let's just write down the sum. Sum of X prime is equal to summation AV, V is in V, plus summation E, exactly one endpoint in S AE. Okay, so let's just write this down. So AV, so there are, so v, not V in V, V in S, I'm sorry. Uh, so this is basically cardinality of S, which is k. So k into 4 power m. So remember, that's how we defined AV. Okay. So 4 power m will occur exactly k times. Okay. Plus summation E, at least one endpoint. Okay. So now what is the remaining value here in AV? You look at all edges incident on V and take the corresponding AE. Okay. Now if you look at this set, so what is covered here in AV? You look at edge. So the edge which has both endpoints will contribute twice, right? So if I have an edge within S, say this is U and V, AU plus AV will have, say this is E, 4 to the E added twice. And for all other edges, this will contribute exactly once, but that is compensated for here. Okay. So what we have is both endpoints in S, two into 4 to the E plus 4 to the E exactly one on endpoint, plus this value. So this is the expansion of this here. Now this value expands to this summation E exactly one endpoint in S A. So this basically sums to k into 4 to the m plus 2 into summation I equal to 0 to m minus 1 4 to the I equal to t. Okay. Yeah, so this is one direction. I'll take a short break, so we'll have another video for the second part. Okay, so the converse direction. So I'll stop here now.